and binary codes for edit errors.
Okay, thanks for the introduction. The title is Deterministic Document Exchange Protocols and Almost Optimal Binary Codes for Edit Errors. In this work, we will study two basic problems. So the first problem is the document exchange protocol. Suppose there are two parties, Alice and Bob, and Alice has a string x of length n, and Bob has a string y of length n prime. And there is some generic metric that bound the distance between x and y by some parameter k. And the objective of this protocol is to allow Bob to learn Alice's string x. So to achieve this, Alice first apply a sketching algorithm to his string x and obtains a very short string sk. Then Alice sends this short string sk to Bob. And Bob will use this string sk and his own string y to recover the string x. And the size of this string sk is called the sketch size. Our objective is to design such a protocol that minimizes the sketch size. The second problem we study is the error correcting code. It is essentially closely related to the previous problem. So suppose you have two parties, and one party has a string x prime of length n, and you want another party to learn this string x prime. The two parties are linked by a noise channel. So to achieve this, one party first encode her string x prime into a longer string c, and we call this longer string c as a code word. So one party sends this code word through this noise channel to the other party, and the other party may receive a different string c prime. But there is some generic metric, and this metric bounds the distance between c and c prime by some parameter k. And the other party will use a decoding algorithm to c prime, and he will obtain x prime. So there are two parameters we care about here. So the first parameter is the redundancy, which is defined as the length of the code word minus the length of the message. And the second parameter is the information rate, which is defined as the length of the message divided by the length of the code word. And our objective is to minimize this redundancy, or it's essentially the same as maximize the information rate. And here is some applications about these two problems. So the first application is about the document exchange protocol. So suppose you have a server and there are some clients. And at first, there is a file on the server. So the server first sends the file to each client, and so that each client has a copy of the file. But later, the client may modify its own file, so their files may be different. And so later, if the clients want to synchronize on their files, they can perform a document exchange protocol. And there are also many other applications about the second problem, the error correcting code, in the internet protocols and DNA sequences. So in this work, we care about a special kind of metric, which is the edit distance. So giving you two binary strings, the edit distance between these two binary strings x and y is defined as the minimum number of insertions or deletions transforming x into y. So for the example on the right-hand side, the edit distance between these two strings is 2. And another metric we will use is the Hamming distance. So also suppose you have two strings, binary strings x and y. And the Hamming distance is defined as the number of different bits in the corresponding indexes. So for the example on the right, the Hamming distance between x and y is 2. And the main differences between the edit distance and the Hamming distance is that the edit distance will cause a shift on the substrings. So for the example, the substring 101 is both appear in the both strings, but their positions is different. So this will cause a lot of Hamming errors. So, and one Hamming error can be considered as one insertion after one deletion. So the edit errors are more general and harder to deal with. And in this work, we only focus on the codings and the document exchange about the edited errors and the strings of a binary case. And for the case of the Hamming errors, these two problems are extensively studied. So as you can see in this table, we have constructions from the Reed-Solomon code and the algebraic geometry code. And for the construction from the Reed-Solomon code, the construction almost meets the lower bounds, especially for the case when k is small. And for the construction from the algebraic geometry code, the parameters already meet the lower bounds. But for the case of edited errors, our knowledge is very limited. We have constructions from of the error correcting code with redundancy that is meets the lower bounds for the constant k, and this construction only works for constant k. And we have other constructions that has much larger redundancy. And for the error correcting code, for the edited errors, the information rate is far from the optimal bounds. And for the document exchange protocol, we only have constructions, we only have deterministic constructions with sketch size much larger than the lower bounds. And randomized protocol that is a log factor larger than the lower bounds. So in this work, we improved such a situation. The first result is that we have a construction of a binary error correcting code with matrix size n, and the code word length n plus big O k times log n. So this is optimal when k is equal to n to 1 minus alpha for any constant alpha greater than 0. And our second construction is a binary error correcting code with matrix length n, and can correct up to k, which is equal to epsilon n edited errors with rate 1 minus O tilde epsilon. And this is a square root. This is a square improvement over the previous 1 minus O tilde square root epsilon n result. And the code word length and the redundancy size is only a log factor larger than the optimal bounds. Our third result is a deterministic document exchange protocol with sketch size big O k times log square n over k. So this is a log factor larger than the optimal, and but it's a deterministic algorithm. And here is the overview of the high-level ideas in this work. So the first observation is the edited errors will cause the loss of index information of these substrings. So the main point is to recover this right index information of the substrings. So to achieve this, we first partition the strings into smaller blocks. So in detail, we first choose a fixed pattern and try to match the substrings of X with this pattern, and use these substrings to partition the string X. Then we apply, for each block, we apply a hash function, a special kind of hash function we call epsilon synchronization hash function and epsilon self-matching hash functions. And then we will use the hash functions and the hash values to perform a match between these two strings. And we expect these matches can provide the right index information about the substrings. And lastly, we de-randomize these constructions using pseudo-random generators. So we first show that we can reduce the construction of error correcting code to the construction of the document exchange protocol. Then we will only focus on the construction of the document exchange protocol. So suppose you have a message X prime. Then you can perform a document exchange protocol and obtain a very short sketch of X prime. Then the idea is to simply attach this sketch to the X prime and form a code word. But we need to protect this sketch from the edited errors. So we encode this sketch using a symptotically good code for edit errors. And this is given by the work of Schurman and Zuckerman. Then we attach these encodings with the original message x prime and denote this new string as a encoding of x prime. So later, we only need to focus on how to construct these document exchange protocols. Our observation is that we can construct a better document exchange protocol if we assume the input string is uniformly random. So the construction actually consists of 2 stages, and this is stage 1 on Alice's side. So we choose a fixed pattern P and try to find all the appearance of P in the string X. And we carefully choose some of the appearance of string P in X as the starting and the ending points. And we use these chosen matched substrings to partition the string X into smaller blocks. And we prove that with high probability, the size of each block is bounded by some polylog n. And any 2 substrings of length b, which is equal to big O log n, are distinct. So after partition X into smaller blocks, let's denote the length of each block as length 1, length 2, etc. Then we take the prefix of each block. And since any 2 substrings of length b are distinct, so all these prefixes are distinct. Then we iterate on each block, and we take the prefix of the current block, the prefix and the next block, and the length of the current block into a triple. And we iterate on all the blocks and obtain many triples. We put these triples into a set V, and Bob can also do this for his string. So Bob will also obtain a version of V. And we prove the differences between these 2 sets is bounded by big OK. So Alice can further send a sketch to Bob to correct this set V. So after receiving this correct set V, Bob will first create an empty string x tilde. And then Bob will gradually fill the content of this x tilde, and hopefully x tilde will equal to x. So given the set V, Bob will recover the partition of x using these triples. And then Bob has his own string y. So for each block, Bob will try to match the prefix in his string y, and then fill the content with the matched substrings in y. And but some blocks is incorrect filled or unmatched, and we will further correct them in the stage 2. So the stage 2 consists of a constant number of levels. And in each level, Alice will use hash functions and values to correct blocks in each to correct blocks. And this is stage 2 on Bob's side. So given the hash values and the functions, Bob will perform a maximum monotone match between his string y and the string x tilde. So we say a substring in y is matched with a block in x tilde if these 2 substrings is mapped to the same hash value under the hash function. And then Bob will use the maximum monotone match to fill the content of x tilde using the substrings in y. But note that some of these matches is incorrect, and also there might be some unmatched blocks. So our objective is to design a special kind of hash function such that the number of incorrect blocks is bounded by some big OK. And so we introduced the definition of the epsilon synchronization hash function. So this is inspired by the recent work of synchronization string given by Hupler and Sharashby. So we first defined the Z-shape. The Z-shape means 2 other junction intervals of length L1 and L2. And the interval L1 is defined on the partitioned version of X. And L2 is defined on the original string of X. And we say a series of hash functions, phi1, phi2, etc., is a series of epsilon hash functions about string X. If for all such Z shapes, the number of matchings in each Z shape is bounded by a constant fraction times the total number of blocks in these two intervals. So the total number of blocks in these two intervals is L1 plus L2 over T. And we prove that such hash functions have the property it can both achieve a very small hash value size and also a small number of collisions on X itself. So this is the construction of a document exchange for a uniformly random string. But can we remove such a uniform random string assumption and construct an error correcting code for any message X prime? So the idea is given the input message X prime, we first XOR it with a pseudo-random generator with seed R. Then we obtain a new string X. Then we use the document exchange protocol to compute a short sketch of X. Then we concatenate the sketch with the seed R. Then we encode this part using a symptotically good code for edit errors. And we concatenate this sketch part with the message X and define this new string as the encoding of X prime. So this is the construction of the error correcting code. And we have a natural open question. Can we construct optimal error correcting code and document exchange protocols for all parameters K? Thank you.
Okay, we have lots of time for questions.
Right.
Does this work for any distance? Because this is an XOR, right? So how does it interact with?
Yeah. So.
Maybe it's trivial, just like.
Yeah. So we XOR with a pseudo-random string, but we also send this R in the encoding. So when decoding, we first try to recover the string X, then we XOR the string X with the pseudo-random string.
Any other questions?
Sorry?
So there was a game round, the paper that you cited.
Yeah.
They computed an encoding some message that they sent from the place to the hard drive. They computed in a streaming fashion that they assume that the input is sent to them county by county, and then they can compute the encoding on the fly.
Yes.
Does the same apply to your encoding, or can you do it in a streaming fashion?
So I think she's talking about the sketching algorithm, splitting algorithm in that paper, but right now our instruction does not have that property.
There was, one more question.
What is the encoding and decoding time?
It's both a polynomial.
But because with Schulman's equivalent, they also get linear time encoding, right?
Yeah, but our encoding and decoding time is not linear, but it's a polynomial time.
So do you think it can be made linear?
I don't think it can be made linear very easily.
Expander base put some value between them.
Might be possible, but yeah. There are some difficulties, yes.
Any final questions? Yep.
Sorry? Okay. Yeah, you need to for some properties we want from the string X. We need some nice properties of uniform random strings. You can read the paper.
All right. So let's thank the speaker again.